Welcome to IGCSE Survival Kit by AZ. Subscribe now and survive IGCSE.
GCSE Warriors, how are you doing? Today we will be solving 0625 Physics Paper 6, February-March 2025. Please stay focused. This is the most recent paper, so you must at all costs do this paper, or even watching this video might be very helpful for you. Okay, so now let's start with this paper. I want you all to pay very close attention to all the questions, and please don't forget to subscribe the channel if you find this video helpful, and comment down any tips you have to improve if you think I have to improve. Okay, a student investigates the behavior of a spring and then uses the spring to determine the mass of an object. The practice is shown in figure 1.1. Okay, there's a clamp, there's a spring. So what he's trying to do, he's investigating the behavior of a spring. Okay, and he uses a spring to determine the mass of an object. Okay, he hangs this object and he's trying to get the mass. So the student suspends a mass of 100 grams from the spring. She measures and records in table 1.1 the stretch length. Where is table 1.1? Okay, here we have table 1.1. The stretch length of the spring as indicated in figure 1.1. All right. Describe two techniques for measuring the length of the spring to ensure an accurate reading. You may draw a diagram. So about diagram, what you can do is you can draw this exact same diagram. You can draw a spring. Okay, I might not be able to draw it exact. Okay. This is not exactly how you will draw it better, more accurately, and then you can keep a ruler and mark the point where you will be reading, okay, and you can draw some scales, okay, and then mark your eye level, which must be perpendicular to the scale reading, okay, and then over here again you can mark your eye level too. And okay, so what are the techniques used for measuring the length of the spring? Always when there's any improvement, any technique, most of the time you can write that. Avoid parallax error, keep the line. Okay, so when using meter rule, keep the line of sight of the eye. Okay, it is line of, not sight, it is line of sight, S-I-G-T-H. S-I-G-H-T, sight of the eye. Perpendicular to the scale reading to avoid parallax error. This is something which you should have been memorized by now to ace good marks in your exam. Okay, ensure that ruler is vertical. Of course, you need to make sure that the ruler is vertical, and you can do that by using, because you know the ruler can be tilted a bit, right? So it can give you inaccurate reading. To make sure it is vertical, you will use a set square. Okay, and it should be, of course, parallel to the string. Parallel means two lines that never meet. You all must be knowing this. Okay, so use a set square. The set square should coincide with the vertical edge of the rule. Okay, that shows the rule is vertical. Another technique you can also write here is that erase all this. Okay, you can use a protractor, and if the 90-degree edge of the protractor coincides with the vertical edge of the rule, then the rule is vertical. All right. Next, she repeats step A for the values. M mass is equal to 200 gram, 300 gram, 400 gram, and 500 gram. Her readings are shown in table 1.1. Okay, so they change the mass and then she measures the length. Okay, so plot a graph of L, length per centimeter on y-axis, and mass per gram on x-axis. Okay, so this is how I have drawn the graph. I have taken L per centimeter, length per centimeter on the y-axis. Okay. And I have taken the mass per gram on the x-axis, and I have taken the scale 0 to 500 because this said that the origin must start at 0, 0. So this is how you will be doing it. This scale of 3.5, 7, 10.5, 14, 17.5, 21. This is which is the even scale. This is the scale which is even. You can take whatever scale suits you the best. Okay. Now I have drawn the line of best fit over here, which passes through as many points as possible. Okay, next, use your graph to determine the length L0 of the spring with no load on it. So basically, the line which you will draw will go from here to here, right? So what you are going to do to find when no load is there, you will extrapolate the line, right? It will go from here to here. Wait, let me show it to you. Yeah, it will go from here to here. So you will just extrapolate the line, that is extend the line, and you will check where it cuts with the y-axis, sorry. Okay, so load is 0 over here. All right, wait. Load is 0 over here, and you check where it cuts with the y-axis, where it meets the y-axis, and what we get over here is 2.45. The answer can vary based on the graph which you have drawn, based on your own graph. All right. Okay, now next you have to, an object X is suspended from the spring. On figure 1.2, measure the stretch length Lx of the spring. Okay, what I got over here is basically 9.5 But you can take your ruler. All right, you will need to place your ruler over here and make sure the readings, you read them properly, and you read from this to this what is the reading, and you will measure it. This is a really easy task and can gain you marks. Just make sure to keep your rule vertical. It's an easy marks gaining question. Okay, next. Use the graph and your reading from DI to determine the mass mx of object X. Show clearly on the graph how you obtained your answer. Okay, let me take you back to my graph. Okay, so the length I got in the previous question was 9.5. So I will check on my graph where this 9.5 length, okay, where we get the mass for this. So you draw a line from 9.5 and you touch the 9 and then you drop it downwards and you check where it cuts, where meets the x-axis. For me over here, it is 190. Okay, 200 minus 10, 190. So it can vary depending on your graph again. Okay, now two students measure the mass of another object using the same method and apparatus. One student records the mass as 132.6 gram. The other student records the mass as 130 gram. State and explain which answer has more suitable number of significant figures for this experiment. Okay, so the answer for this is 130 gram has more suitable number of significant figures. The reason for this is that recording a value like 132.6, which has 4 significant figures, implies a level of precision that the apparatus may not support. For example, the apparatus which you use, the force meter, okay, you can say, or yeah, the force meter, it can't give you a value, or if you're using a balance or anything like that, it can't give you a precise value of 132.6 gram because it has a higher level of precision that the apparatus may not support. So 130 gram is a better reading. Okay, moving on to the next one. A student investigates the effect of insulation on the cooling of water. He uses the apparatus shown in 2.1. Okay, we have 2 beakers here. All right, and then there's a thermometer and you place the beaker probably over here. Or yeah, that's how you can do it. Okay, beaker A is covered with a material that is a thermal insulator. Okay, we can see there's insulation here, and beaker A is covered with beaker B. Yeah, wait, it's covered. Beaker A is covered with the material that is a thermal insulator. Okay, and beaker B is identical to beaker A, but it has no insulation. So you can see the only difference between these two beakers is that this has an insulation and this has no insulation. Okay, no insulation. My handwriting, I always tell you to deal with it in every video. Anyways, this has no insulation. Record room temperature theta r shown in the thermometer. So if you see here, it's one scale up from 20, so it's going to be 21. How you can read this is always make sure, okay, always make sure you check how many scale readings it has. It is 1, 2, 3. Well, it is basically 10. So 30 minus 20 divided by 10. 30 minus 20 divided by the number of spaces 10 will give you how many like is one scale. So it is 1. All right, so 21 degrees Celsius. Okay, now let me just erase all this. Okay, describe one technique used to ensure that the room temperature reading is as accurate as possible. So one technique you can use, this is a very common question. We already discussed this before in the ATP analysis. If you have not watched it, please do watch it, as it is a very helpful video discussing all the guidelines for physics paper 6. Okay, so describe one technique used to ensure that the room temperature reading is as accurate as possible. Those who have watched those videos must be knowing. You should write here that keep the line of sight of the eye perpendicular to the scale reading to avoid parallax error. We have already discussed all this, but wait, we can't write these 3. The reason is that it is a room temperature reading, so don't include these. You can only write this keep the line side of the eye perpendicular to the scale reading to avoid parallax error. This is when you have a beaker. Okay, when you're measuring it in a beaker, but this is for the room temperature, so make sure don't write any of these. The line of sight, the parallax error will be the better option to go with. Okay, the student pours 200 centimeter cube of hot water into beaker A and records the temperature theta at time t is equal to 0. He records in table 2.1. Okay, here's table 2.1. The temperature of the water in the beaker every 30 seconds. Okay, yeah, every 30 seconds. The student repeats the procedure for beaker B. Okay, so first he pours hot water in this beaker A. All right, in this beaker A, he pours hot water and then he measures the temperature at t time is equal to 0, and he measures it every 30 seconds. Then he repeats it for beaker B. It is important that the temperatures are recorded at exactly every 30 seconds. Describe a technique which will make it easier for the student to do that. Okay, they haven't mentioned that they have placed the thermometer in the beaker. Here we can only assume that it is placed here. All right, so what you can write here is that place the thermometer in a beaker and use a stopwatch. Now note the temperature of thermometer after every 30 seconds shown on the stopwatch. Okay, when you will keep a stopwatch, whenever it's 30 seconds, you will note the temperature on the thermometer. Again, after 30 seconds, note the temperature on the thermometer. Okay, so with this way, you won't have to remove the thermometer from the beaker and then again, and after 30 seconds, add it back. This can become very difficult and tricky. All right, next question. Write a conclusion stating whether the insulation affects the rate of cooling of the water. Justify your answer. Okay, justify your answer by referring to values from the results. We have to state whether the insulation affects the rate of cooling or not, and make sure you're justifying your answer. Very important, because most of the students miss that. So the thing over here is that beaker A, with insulation, the final temperature reached is greater. The reason is that the temperature lost to the environment is less due to the insulation that is around beaker A. But for beaker B, the temperature reached is low because it loses more heat to the environment, whereas this loses less heat to the environment. All right. So what you will see here is that insulated beaker A cools more slowly than uninsulated B. Okay, if you cool more slowly after 180 seconds. Now this is how you're justifying. This is how you wrote a conclusion, how it affects. Okay, it cools more slowly. Now you're justifying your answer. Okay, how do you justify your answer? You need to take readings from the table. Okay, after 180 seconds, beaker A, you will basically write beaker A over here. Okay, beaker A is at 85.5 degrees Celsius, while B is at 83.0 degrees Celsius. Over 180 seconds, what's written here? Yeah, beaker A's temperature drops 7 degrees Celsius. Basically, see, if you subtract 92.5 with 85.5, the temperature drop is 7 degrees Celsius. Whereas for beaker B, 93 minus 83 will give you 10 degrees Celsius. So it is a 10 degrees Celsius drop in temperature. So you will say insulation reduces the rate of cooling because beaker B cools more, as we stated earlier. Okay, this we got to do it. Okay, so calculate the average rate of cooling. These are really simple mark scaling questions. Make sure you never mess up these questions. You can easily attain the full credit in these questions. Okay, paper 6 is very easy. Make sure you practice a lot and watch the guidelines of the video. After watching that, continue practicing. Hopefully, you will be getting the full marks, inshallah. Okay, so let's do this. Average rate of cooling. What is this? Calculate the average cooling rate x1 during the first half of the experiment of the water in beaker B. Use the readings for beaker B from table 2.1 and the equation. This is the equation we have to use, where time t is 90. Okay, they have given the value for time t, and we have to take these two values from the temperatures of the water in beaker B at time 0 and 90 degrees Celsius. Okay, let's check. What is it at 0? For 0, it is 93, and for 90 only they've asked, right? Yes, 90. For 90, it is 87. So what we will be doing is theta 0 minus theta 90. So what we are getting here is theta 0 is what? What was it again? 93. All right, it's 93. And theta 90, theta whatever. Okay, theta 90 is what? 87. 87. Okay, so what we got to do is we just have to subtract it. 93 minus 87 over 90. So you will get this as 6 over 90, which is equal to 0.66666. So you can round it off to 2 SF, 0.67. So you also have to include the unit. Don't forget it. You will not get the full 1 mark. 0.67 degrees Celsius per second. All right, because this is theta is in degrees Celsius and temperature is in second. Okay, now let's move on to the next question. Calculate the average rate of cooling. Oh my god, again. Okay, x2 during the second half of the experiment for the water in beaker B. Don't mess up beaker A and B. Okay, use the readings for beaker B from table 2.1 and the equation. Now we need it for theta 90. Theta 90 we already have it, 87. Let's check what it is for 180. It is 83. Okay, so for theta 180, it's 83. So what we're going to do is 87 minus 83. The hell? Okay, great. Yeah, minus 83 over t. What do we have for t? At 190 seconds and 180 seconds. Okay. Yeah, we have t here, 90. Okay. Over 90 is going to give us 4 over 90, which is equal to what? 0.044, and it goes on. Okay, so you can write it as 0.044. 0.044. Again, the same unit in degrees Celsius per second, because temperature is measured in degrees Celsius and time in seconds, so degrees Celsius per second. Okay, next. A student suggests that for this type of experiment, the temperature of the water in each beaker at time t is equal to 0 for the same, Wait, a student suggests that for this type of experiment, the temperature of the water in each beaker at time t is equal to 0 must be the same for the comparison to be fair. Okay, so they're telling that the starting temperature, that is t is equal to 0, must be the same so that it can be compared. Okay, so use your answers to explain whether this is necessary. Yes, this is necessary. So the average rate of cooling, so the average cooling rate every 90 seconds is same, right? Because average rate of cooling rate is the same, and we can, like, for each beaker, the cooling rate should be the same for after every 30 seconds, right? For beaker A and beaker B, right? But no, 0.067 degrees Celsius per second is not equal to this. It should be equal because okay, this is 7, guys. Don't concentrate 1. Okay, because for every 90 seconds, the rate of cooling must be the same, the average rate of cooling. Okay, quite a lot of messy stuff over here. Messi Ronaldo. Okay. A student wants to eliminate from the comparison any thermal energy lost from the surface of the water. Suggest a change to the equipment which will do that. So now don't mess up. Don't start writing use a polystyrene cup, blah, blah, blah. They have already insulated it. What they're saying is that any thermal energy lost from the surface of water. Please read your question carefully. So you have poured the water. How can you prevent from the surface of the water? So the simplest thing you can do is just put a lid over here. Okay, so use a lid of the same thickness for both the beakers, of course. Same thickness is not necessary. You can just try to use a lid to cover the beakers. Okay, to cover the top of both beakers. Okay, suggest what effect this change will have on the cooling rates of the water in beaker A and B. So they're asking what if you put a lid, what will be the effect on the rate of cooling of water? Cooling rate of water in beakers. So where basically the cooling rate will decrease. Why? Because when you put a lid on top of beaker, what is it going to do? It is going to prevent evaporation. Right? It's going to prevent evaporation, so liquid will not easily evaporate, so the cooling rate will decrease, right? The way you can reduce the cooling rate is to use insulation and of course a lid. So yeah, lid will prevent evaporation, so the cooling rate will decrease. Okay, a student investigates the refraction of light by transparent block. The student's read trace sheet is shown full size in figure 3.1. Okay. Now, what you have to do over here for this type of experiment, for this type of question, it's an easy mark gaining question. Make sure your pencil is sharp, okay, and you keep your scale properly whenever you're reading the ruler, okay. Now, the student places and read the questions, of course, very carefully, because most of the people, they don't read the question. They miss some point and then they are lost in the next part when they're asked to, like, measure the distance and all. Okay. A student places the transparent block ABCD near the center of the ray trace sheet as indicated in figure 3.1. Draw a normal to point M extending above AB. Label the upper end of the normal with letter L. Okay, I'll show you later how I've done it properly, but here, for now, draw a normal to point N extending above AB. Okay, so you will draw a normal at point N. It should be extending above AB. Any other requirements? Okay, label it with L. Okay, so this is point N, right? This one is point N. So what you're going to do is just draw a straight line. I can't draw it straight, but make sure you all draw it straight. And it should be extending above AB. Okay, we have already done that. And what else do they want us to do? They want us to label the upper end with L. Okay, so you label this upper end with L. Don't make it too long that you don't get space for labeling, all right? So, next. A student draws EN as shown in figure 3.1. Okay, they've already shown us EN is drawn, all right? And, yeah. Measure the acute angle between the lines LN and EN. An acute angle is an angle of less than 90 degrees. So what you're going to do for this question is that you will place your projector, okay? You'll place your projector this way, all right? And then you will start measuring from here. This line should coincide with this line. And then you start measuring from here. What measurement you get over here? Okay, what I got over here is 40 degrees. Alright, it depends on your printout also. If you get the exact print according to the question, what it is required, so you might be able to match the mark scheme, but for this we don't have a mark schemes anyway. Next, the student places 2 points P1 and P2 on line EN as shown in figure 3.1. Okay, wait, just let me erase this protractor. Okay, so there, this is P1 and this is P2. This is shown how they have drawn it. Okay, now measure the distance between these. Okay, so again, this is easy. You'll just place your ruler like this and you'll measure the distance. Easy baby questions. So you get 3.8. Now, this question, we already discussed this. in our previous video again. State whether the two pins are at a suitable distance apart for accurate ray tracing. Explain your answer. Basically, they're not at a suitable distance apart. The reason is that they're not at a suitable distance. The reason is that this is 3.8 and we have discussed that it should be greater than or equal to 5 centimeter. So the pins must be at a longer distance of 5 centimeter or more to get more accurate results. 3.8 centimeter is too short. You can also add that percentage error can happen or it can be reduced by this. Okay, if you use a 5 centimeter long. Anyways, next, the student views the images of P1 and P2 through the block. Okay, he places two pins P3 and P4 so that in the pins P3 and P4 and the images of P1 and P2 will appear exactly behind one another. Okay, you can do this experiment in the lab and you can know what you're seeing over here. Okay, now draw a line through P3 and P4. Extend the line to meet CD. Okay, here's P3 and P4. You're going to draw a line and you're going to extend it to meet CD. Okay, I can't draw it exact over here, but make sure you draw it straight and thin and sharp with a sharp pencil, of course. You can deep sharpen your pencil again and again during the exam, all right? Of course, don't waste too much time, but make sure it's sharp. Carry 2 or 3 sharp pencils. That can also work so that, you know, when one goes blunt, you can just take out the other one. Okay, so we have drawn this line, extend this line to meet CD. We have done that. Label the point at which the line meets CD with letter F. Okay, you label this as F. All right, next, label the lower end of this line with G. Oh my God, okay. Yeah, I told you don't extend it too much. Anyways, this is G, okay. Now, yeah, extend the line EN to approximately 5 centimeter below CD. Extend the line EN. Okay, what you're going to do is just take this line and EN. All right, extend it below 5 centimeter of CD. All right. Now, what do they want us to do here is, they're going to tell us to label, of course. Yeah. Okay, to 5 centimeter below line CD, label the point at which it crosses CD with H and lower end with J. At which it crosses CD, which is CD. Yeah, CD is here. Don't label AB, okay? CD is H and the lower point with J. All right. JK rolling. Okay. Measure the acute angle between lines CD and GF. Okay, CD and GF. Where CD is here and GF is here. So it's an acute angle, right? They've mentioned it's an acute angle. Acute angle, remember, acute angle means it is less than 90. They've given it here, right? Yeah, it's less than 90 degree. So you can't keep your protractor here and think that you can start measuring from here because it's going to be more than 90 degree. So what you're going to do instead is keep the protractor at this position and start measuring from here, okay? And check what you get, what angle is made over here, okay, with GF, okay? And we get here 53 degrees. It can vary based on the way you have printed your paper. Okay, wait. Let me just undo all this. Okay, next. Next one is measure the acute angle between line CD and JH. Between line CD and JH. Again, you keep the protractor over here. What the hell? Wait, yeah. You keep the protractor over here, okay? And you measure the distance, the angle from here. You start measuring it from here, okay? You don't measure it from here because it's going to be greater than 90 then. Okay, you measure it from here and you check what angle you get over here. All right? So, let's see what I got. I have got here is 50 degrees. Okay. Now, the student suggests that the angle, I don't know what they're trying to say. They're pretty trying to say alpha or whatever. Should be equal to angle P, beta, whatever. Okay, state whether your results support this suggestion. You will say yes. Do you know why? Because what you're going to do whenever you're given two values is you're going to check if they lie within the range, within the limits of experimental accuracy. So what you're going to do is you're going to do 50. Okay, you're going to add it with 110%. Okay, so 100 plus 10. I'm telling you the method so it's easier for you. Over 100 times 50. What you're going to get, I suppose, is 55. Okay, let me just do it. 100 plus 10 over 100 times 50. Okay, yeah, you get 55. Okay, so this will be equal to 55. All right, and now the range we have is from 50 to 55. Another way you can use is you can do 100 instead of plus. You can do minus over here, and if you're going to use the, what do you say, 53, right? And then you do 53, so you're probably going to get something like 50 or something. I don't know. Okay, so this is actually what you'll get here is, okay, here what you're going to get is going to be right? Give me a minute. Here what you're going to get is going to be 47.7. All right. So 50 to 55 or 53 to 47.7. These are the limits of experimental accuracy. So yes, if you take 50 and if you check 53 fits here, yes, it is between 50 to 55. If you take 53 and check if 50 fits here, so yes, 53, then you go on decreasing, so you will get 50 over here. All right. So this is how you check if it's within the limits of experimental accuracy. All right. So yes, the results support this suggestion, and you will say that the values, this and this, always quote the values, lie within limits of experimental accuracy. Don't forget to write this statement. Okay, memorize it. Okay, root memorize it, do whatever you want, just remember this. Okay, that is within 10% of each other. You will always write this statement. All right, you will always write this statement whenever they ask for justification for this type of questions. Just change the values if they lie within experimental accuracy, of course. If they don't, then just write the values this don't lie within the limits of experimental accuracy, that is within 10% of each other. Just add a don't. Okay, so it's a sample answer you can memorize to attain full marks. Okay, describe 2 techniques to use in this type of experiment to ensure results are accurate. Okay, I've given you 3 techniques. This is basically a ray trace diagram experiment. You have already discussed this yesterday as well, that use thin pencil lines to draw the ray. Okay, use thin pencil lines, of course, it's going to be more accurate than view from the bottom of the pins or the bases of the pins, and ensure pins are vertical. Very repeated question, please. Make sure you know all this. Okay, you have to write any 2. Don't start writing 3 over there. Okay, any 2. If you write 3, though, you never know. You know, the examiner might deduct marks. All right, because I have seen candidate responses in which you have written, the candidate has written 3 or 4, and the examiner, like, instead of 2, the candidate has written 3, and the examiner is like, the candidate is not sure with his answer, so straight away deduction of marks. All right, so just one reason why different students all doing this experiment carefully may not obtain identical results. Okay, all of the students are doing the experiment carefully may not obtain identical results. You can see pencil lines marking have finite thickness, like some are using thick pencils, some are using thin pencils. So you know when they keep the protractor and the scale reading and all, so it's not that accurate. Okay, experiment question. Many students are scared of this. Do not need to get scared. It's a simple question compared to chemistry and bio. It's simple because see, you have the bullet points already given here. Okay, a student investigates the resistance of a wire. Plan an experiment which enables him to investigate how the length of the wire affects the resistance of the wire. So length and resistance is what we are going to be dealing with. Resistance R is calculated used from the equation R is equal to V over I, where V is the voltage potential difference and I is the current in the. So the apparatus available: a section of wires, a variable power supply, an ammeter and a voltmeter. List any additional apparatuses needed. Complete figure 4.1 to show a voltmeter connected to measure the potential difference across the wire. Okay, so you have to connect the voltmeter. Voltmeter is always in parallel. Okay, yeah, we've discussed this before in our video. Okay, it's in parallel. All right, and then you can draw this using the scale to just make sure it's good. Okay, and then list the key variables that are kept constant. Okay, wait, explain briefly how to do the experiment. Of course, you need to do that every time. Include measurements to take so that resistance can be determined. Key variables to keep constant. Draw a table, okay, with column headings to show readings. You're not required to enter the readings. Please remember this the most of the time. Actually, always you don't want the readings. Okay, explain how to use the readings to reach a conclusion. For this conclusion, you always do a graph. Okay, you plot a graph and you tell the axis which you're going to take to plot the graph. So the additional apparatus that is needed is a meter rule. Now you use a 10 centimeter length of wire. Measure the length of the wire using a meter rule. It's RE over here. Okay, RE. Anyways, so you set up a wire with the variable power supply, an ammeter, and the wire connected in series, whatever stuff is given over here. Okay, and then voltmeter, we didn't mention about that. Okay, so you have to connect the voltmeter in parallel. All right, you have already discussed this before, across a section of wire whose length is being tested. All right, now keep the power supply at a constant low voltage. Okay, constant low voltage to avoid harming effects. You can add this. Okay, then when the circuit is complete, you got the voltage from the voltmeter and current I from the ammeter, voltage V. Okay, now you calculate when the circuit is complete. You got the voltage V from the voltmeter and I from the current I from the ammeter. Calculate the resistance using the formula R is equal to V over I, like you already told us before. Repeat the procedure. Make sure to write this for several lengths of wire: 30 centimeter, 50 centimeter, 70 centimeter, and 100 centimeter. Okay, repeat each experiment 5 times, and okay, it has to be and over here. And average result. To get more reliable result, always include this point. It's a free 1 mark. And even the graph. In the graph in the end, it's a free 1 mark, so 2 marks are guaranteed. Okay, then I've just mentioned the sign again over here, so just cut it off. Anyways, keep the voltage of the power supply, thickness of wire, and type of wire constant because the asterisk variables have to be kept constant. And this is the table I've drawn. You must draw it like, by following the points. Try to go with the points, but I drew it in the end. Okay, now to reach a conclusion, plot a graph taking length per centimeter. Always this side, okay, always this side will go on the x-axis. The left side, right? Yeah, the left side of the table, and the right side will go on the y-axis. All right, so what you're measuring, right? We have discussed this before in the video. Okay, on the x-axis and resistance of wire per ohms on y-axis, if the graph shows a straight line through the origin, that confirms that the resistance is directly proportional to the length of the wire. All right, so with this we come to the end of this paper. I hope you all are very well prepared for your exam. Bye, take care, and give your best. Make sure to practice past papers. You will all do well. Good luck.